Welcome to this little project presentation for the hackathon that went on last week, the weekend of the 14th, I believe it was, of April, the Interpretability Jam 2.0. So here we have, first of all, Albert, who will present the project on Otelloscope that happened here. And we also have a recording from another team, and I will go through a couple of the other projects that happened last weekend. So we of course just came back from EAGX Nordics and are excited to check these out. So first off, I'll pass it on to Albert and he will take this one.
So recently some interpretability work has been done on the game Othello. So I'll just quickly explain what you need to know about that. You have a board state, as you see here. Each player takes turns placing a marker down in a legal spot. When they do that, some of the other markers flip to the player's color. And the important thing is that which spots are legal depends on the board state in such a way so that the game tree is non-trivial and probably infeasible to memorize. So there was this paper which wanted to see, try to interpret which world models transformer models had. So they trained a model to predict valid moves in Othello. They passed it a series of game moves and trained it to predict a next move which was legal. Importantly, they did not train it to play well, they trained it to predict a next move which was legal. It turned out they had some results which were interesting, but Neil Nanda then did further work on it and found out that you could actually get the board state out of this model from using a linear probe on the 6th layer. So the interesting thing is that the model has never seen a board state. It has never seen a board like you were looking at now. It has only seen action sequences and it has only been trained on predicting actions, but you could still, from the activations of neurons, get out the correct board state with very, very high accuracy. So this means that the transform model has somehow built up an internal world model, which is very interesting in itself. We wanted to look at this and do further work. One of my ideas was to see if this was truly modular. So if it at the 6th layer had a model of the world, then we should be able to remove the rest of the layers. So layers 7, I think, maybe I can't remember, but at least layer 7. Reinitialize them and then train it on a new set of rules, and then it should be able to work. It should be able to train well, even though we do not do any changes to the first 6 layers. This would be very interesting. This would be showing the modularity of a transformer network. Spoiler alert, we never actually got that far. So our first step was to try to start doing interpretability work on this model. We wanted something like Neuroscope for the Othello model. For those of you who don't know, Neuroscope is a tool developed by Neil Nanda, which allows you to, for a series of large or small language models, look at individual neurons. Let's take a random one from a random model, and you can see which pieces of text most activate this neuron, and even which parts of the text most activated. This, of course, does not directly give you mechanistic interpretability results, but it may give inspiration for what to look at. So we wanted something like this for Neuroscope. For Othello. We started working on this, and it took so long that we ended up pivoting away from our modularity experiments and in general our experiments to just working, just making it a goal to create Otelloscope, that is Neuroscope for this model. And that has succeeded pretty well. So let's go up to the so here we have one of the neurons, neuron 255, on layer 2 of the Othello model. Here we have heat maps which tell us which board states this neuron especially activates on. So when we see that B6 over here is very red, that means, since this is the my pieces heat map, that means that this neuron activates especially when the piece B6 is owned by the other player. Since B6 is very green over here, we know that this neuron activates especially when this cell is blank. This does seem to be slightly inconsistent, but all of this is probabilities, so you know. And this is, of course, seems to be a very interesting tool, a very useful tool if you want to interpret this model. So and then down here we have a list of the games, much like for Neuroscope with sentences or text. We have the list of games which most activate this neuron, and you can also see which states of the game, which actions of the game, steps of the game most activated. So you can see at this action it was very activated, at this it was very little activated. And maybe this particular isn't a particularly interesting neuron, but there are many patterns you can see. Maybe you can see here that, like, on the first step, it's basically not activated at all, and then it seems like there's some gradient towards the end where it starts by being activated pretty often, but then becomes less and less activated. Maybe this you could probably develop some hypotheses based on this if you wanted to. On top of this, one question is, which neurons do you want to investigate? So we created this table which lists the neurons in each layer by the variance of their heat maps. So this neuron here is the neuron with highest variance in this heat map, in the hopes that this may be one of the most interesting neurons. Who knows? Okay, so while this is all interesting, for Othello, that has a big caveat in that Othello is not that interesting. Sure, it's a fine game, but like, who cares about this specific model? So our ambition, or at least my ambition, is to develop this into a tool which makes it easier to create these Neuroscope-like tools for other models. This took Espen and me an entire weekend to build, 2 whole days. But it seems like much of what we did could be reused for other models. So wouldn't it be great, instead of having to pay up with 2 whole days of work to be able to use this and get inspiration, you only had to pay maybe 2 hours. That's my ambition, and what I'll try working this into. We have a Neuroscope for Othello, and we have a Neuroscope for some small language models. So figuring out what do they have in common, what are the natural abstractions around this, and then building a tool around that. Yeah.
Nice.
That's it.
Massive. Yeah, and actually we were also, for a paper we just got published, we were thinking about making a Neuroscope-like thing, so maybe that can be a test case for the transformer setup. Nice. Do you have any questions, Matthias?
I wouldn't say I understand enough about this to give intelligent questions. So I prefer to keep shut and keep you in doubt of whether I understand this or not.
And Mango Kitty, do you have any questions? Otherwise, I can probably come up with a few.
No, nothing from my side, but thank you.
Wonderful. Yes, I guess some of the questions are, how would you make it possible? So this is very specialized visualizations for games, right? This is quite specialized visualizations on the logic attribution. Like, logic attribution is pretty general, but mostly for the feature maps there.
Yes.
How would you generalize that? Like, would you just have a bunch of different graphs that people could go for, or?
So the plan, I guess, is that people to some degree can generate their own data, because this is based on like huge PyTorch tensors, and like actually generating that data was not what took that long. What took a long time is building the website. So the plan is that the user provides the probes and some configuration for how to set it up. Maybe, yeah, and then the tool does the rest. Much of the abstraction is still an open question, which is what I'll be looking at. But I think I have some ideas. They're just not really ready to be talked about. I think they'll be more confusing than anything else. Yeah.
Yeah, that makes sense. And you mentioned little activation at the red ones. I think what you might have meant is
negative
high
activation.
negative activation.
Yes, that's what I meant.
Because of course, if it's the absolute activation, that's amount of activation as well.
I agree.
Nice. Yeah, and do you think it will look this HTML like in the future?
No. So that's one of the this is a prototype, which you can also see if you look closely enough. There are a few bugs which I have fixed in the code, but not in this version. And also it looks. I would say it looks nicer than Neuroscope, but not like very nice. So if when I do get going with this, I'll definitely get someone who can actually do HTML styling in to make it nice. Well, early versions probably won't be much nicer than this, but like we that could definitely be changed.
Yeah. Awesome. I think I can imagine that being super useful, because a lot of this MLP stuff seems at the moment to be pretty qualitative, right? Like pretty much,
yes.
Okay, check out these neurons, try to figure out some qualities of them.
So the best, so also like the idea is to help people get to that level very quickly.
Yeah.
So that they can start actually looking at that. So it isn't a feat in itself to be able to look at neurons and look what they do. So you can get there very quickly and actually try and do some mechanistic interpretability based on whatever inspiration you get.
Yeah.
I do have a very basic question. So how do you generate? Like, how do you find out how to representate each neuron? So this is layer 0, neuron 1753. How do you what process leads to these maps? So do you put how do you monitor this single neuron?
Yes. So we use, in this case, so we talked about the linear probes, which were used to, which you could use to get the board state out of the different layers, and we used that to create these. So this is kind of, but not quite, basically like this neuron's weight in that probe. So the probe is basically a matrix. It's basically a linear transformation of the neurons. So if something is very green here, that means that it has a highly positive weight in that transformation, which turns this layer into the board state.
Okay. Yeah, and I guess what it's transformed from. So there are like 3 features. One is white, black, and blank, right? Of the original one?
No, it's
and then
yours, mine, and blank.
Yeah, and then they've been transformed. For this linear probe into the 2, so you can like do some subtraction and addition between these 3 to have either my pieces or their pieces, so that's positive or negative activation there, and the dimension of blank versus not blank pieces.
Right.
Yeah.
Okay, that makes sense.
Yeah. So that's the two dimensions there.
Yeah. The nice thing with linear probes is that you can just do arithmetic on them and get new interesting probes out, right? So
yeah. Good contrast.
Yeah.
Nice. Well, a little hand again. Wonderful. Thanks for the presentation there.
Cool.
I'll take the seat again.
And I don't know, Mango Kitty, if you want to present as well, then you're very welcome to. Otherwise, we also have a video there.
For me, I'm gonna stand down for this one, but
Yeah.
hopefully for the next hackathon I'll have something to show.
Perfect. That sounds good. Okay, then I will jump straight into some of the a pre-recorded one we got from another team.
Examining how dropout affects the phenomenon called superposition in training of neural networks. This project was mostly inspired by one of Neil's 200 problems in mechanistic interpretability, and greatly builds on the work published in the Transformers circuits thread, specifically toy models of superposition, from which we take many of the graphs, in fact, that we will show in this presentation, as well as a lot of the starting point for the source code of our work. To give a quick recap on what was found in toy models of superposition, if we look at the activation space of neural networks, we can consider features as directions in this activation space. And we can look at how these directions align with a privileged basis, or with the basis in which we are, with the basis which we're considering in this activation space. So some features can be non-aligned to any of the basis vectors. In this case, we say that we are in a non-privileged basis. We could be in a privileged basis where some or most of the features are aligned with the basis dimensions. And this is obviously the best case scenario for interpretability, because this essentially means that neurons are monosemantic, and so we can, well, hopefully easily identify what the meanings of these neurons are. And then in the superposition hypothesis, we believe that neural networks are learning way more features than there are neurons available, and so the features are not aligned with any privileged basis, but they are packed and they are in superposition across different neurons in these almost orthogonal vectors in the activation space. In the article, they show how with increasing feature sparsity, superposition starts to be much more prominent in these in the toy models that are trained. In fact, we see that without sparsity, the models simply learn the first n most important features, depending on n being the dimensionality of the activation space. But as we increase sparsity, the model learns that it can efficiently pack more and more features into the space by superimposing them across dimensions. The methods we use are, once again, we try and do minimal modifications to the model proposed by the authors of toy models of superposition. Starting from the data, the data is left unchanged. So we have features with varying sparsities across experiments. We have generally a higher number of features than the dimensionality of our activations, our representations, and we have features with a varying importance. The autoencoder we consider is exactly the same one as in the paper. It is a simple two-layer encoder, one-layer decoder autoencoder with a ReLU activation, and the only modification we do is adding dropout at the hidden before the hidden vector. And one method we use to evaluate the presence of privileged bases in higher dimensional, when we consider models with a higher dimensional activation space, is looking at the kurtosis of the activations. Because obviously it becomes unfeasible to simply plot the directions and look at whether they are aligned or not. This technique is derived in another post, the latest post in the Transformers circuit thread, where they analyze the presence of privileged bases in the transformer residual stream. To not be aligned with any basis, then it means that it would be invariant to any random rotation, and so equivalent to being sampled from a uniform distribution on the n sphere. And a way of sampling unit vectors from a uniform distribution on the n-sphere is to sample their components individually, independently from a normal distribution. This is better explained in the transformer circuits thread. But in short, we can look at the kurtosis of the activations and check whether the kurtosis is that of a Gaussian distribution, so around 3, or whether it's to what extent the tail heaviness of the distribution changes. And when we have a basis that is, when we have activations that are aligned with the basis, we will have a much bigger, a higher kurtosis, and so more tailedness in a curve. With small models, we can visualize the directions, and so these are some experiments we ran. We can already see that when we introduce dropout, we get these anti-parallel features that are learned with these anti-parallel vectors much more often than without dropout. So this is already a sort of a confirmation of the fact that dropout does in fact align the features with a basis. And if we look at the larger models, looking at the kurtosis, we see that, so if we take a look at the blue line, we can see that, which is the model without dropout, this simply reproduces the results in toy models of superposition. We see that at the beginning, with non-sparse features, only 2 of the features or only n of the features are learned, and so we have strong alignment with the privileged basis, and we don't. So obviously the distribution is very much non-Gaussian, but then as we introduce sparsity, the kurtosis falls down to 3, and the distribution of the activations is Gaussian. But we see that with dropout, this effect doesn't really happen. So we maintain superposition occurs in a much weaker sense and much later across the sparsity. And we can see this occurs proportionally with a strength proportional to the intensity of dropout, basically. If we look at the 2 histograms at the bottom on the left, we have the histogram of a model of the activation of a model with strong dropout, and on the right of the model without dropout. And we can clearly see how on the left we have almost a single frequency, almost a single bin contains all the activations. So very much non-Gaussian distribution of activations. The fact that superposition is very much delayed by the introduction of dropout. So these graphs are organized vertically by feature sparsity, with the top left being no sparsity and the bottom right being the highest level of feature sparsity, so where we expect there to be the most superposition. We see that the models without dropout, in fact, so to read the bar charts, each individual bar represents a new feature. The height of the bars represent their norms, so how the intensity to which they are represented in the model, and the color represents the degree to which the feature is in superposition with the other features, with yellow being the highest possible, and blue being completely independent from the other features. We see that without dropout, very quickly with increasing sparsity, features start to be in superposition with each other, to the point where we represent many more features than we have dimensions, and they are all in superposition. And with a dropout of 0.5, we start having a bit of superposition with sparsity, but the rate at which superposition occurs is, with increasing sparsity, is much, much slower. And in fact, we maintain some features that are almost independent from the other features, even with the highest level of feature sparsity that we've considered. By the way, this graph, once again, is taken from, and the source code for these graphs is taken from the toy models of superposition work. And so why does this happen? One intuitive explanation that we've had, that we thought of while working on this, is that dropout is exponentially more likely to perturb at least one of the neurons that are used by features in superposition. And so this incentivizes the model to learn to place as much information on individual neurons, and so aligning them on a privileged basis, simply in order to lower the chances of the representations being perturbed during by dropout during training. Thanks, everyone.
Well, let's give this video a little clap as well. So I think that was super interesting. Very fascinating that you end up with. It would be great to have the authors here actually, but very fascinating that you end up with something along the lines of dropout incentivizing non-superposition. So instead of it seems like we can do a lot of interesting things with that to ensure a privilege basis. All right. So here are an array of some of the different projects that were made. We've selected a few here. Some of them wished not to be shown. So this project by Mateus and Jay, they improved the in the transformer lens library. I guess I can also just find that. But Neil Nanda has made this library called Transformer Lens, and Mateus and Jay has then contributed to it. And maybe we can even see. Let's see here if there was anything. Yes, change head detection demo to install correct transformer lens package. So they've done a bit here and there to make the heads, the attention head detector work even better. So very awesome job from them. And then we have one project that requested not to be shown, and we have a project exploring the Otello GPT model. So there are some key observations here. So the model knows the cell of the current move is not blank by a token embedded. It knows the layer 0 attention layer already knows with 9% accuracy the blank or not blank board state. So this is super fascinating, right? Like looking at some of the attention heads here. And layer 1 to 4 attention layers increases the blank not blank classification accuracy to 99%. So it very quickly becomes quite interesting model of the Otello board. And then the MLP layers seem not to relate to blank not blank classification, and a few other insights down here. So we can see the visualizations that they used, and you can see the central 4 squares are there's no activation there because this represents the Otello board, and the central 4 squares they are filled in the beginning as well. So here's a lot of error rate of blank probes, blank versus not blank here. Very interesting. And would like to dive deeper, but we should have the authors here the author here to explain themselves as well. And the next project, we have the Otello layer scope. So this is sort of replicating some work by Stefan Heimersheim. So I believe Victor worked on this, and from this team that has actually submitted 2 different projects. And it builds on work that Stefan Heimersheim made for another interpretability hackathon, where he looked at basically creating an interactive website for exploring the transformer models. And this one then does the same for Otello, so a bit in the style of what we've been working on. So here we can see the prediction that it tries to make for the next token, depending on a lot of things, and we can look at the attention pattern and the residual stream patching and a few other things. So that I believe there is a link to it as well, but maybe it will have to start up, so let's not play too much with that. And another project, this is again going back to the Otello scope actually. So this is the report, you can see the visualizations here. And I want to just, because this is focused, Albert's talk was focused a bit on what the future of it is, but there was actually also done a few qualitative investigations into what happens inside the models, and based on just like looking and using the Otello scope. So, for example, it seems that some neurons activate to very few moves, like less than 5%, while others activate to 50% plus. And this seems pretty bimodal and would be up for like more research, right?
What does bimodal mean?
Just that you have a lot in lower than 5%, and you have a lot in like more than 50%,
right?
And not necessarily much in between, or at least it's prescient on those 2 boxes. And most neurons that activate to a lot of moves also activate differently to alternating moves, which supports the so basically if you the input is the game moves by each player, so it plays itself, right? And then you can see that it'll activate a lot to this move, not the next move, and then a lot to this move and not this move, and so on. So this is alternating activation, and this fits the hypothesis that it doesn't actually activate to the white or black pieces, but more to the state of my pieces, which changes every turn, right? So that's something that you can see by just exploring all the neurons. And the first move is consistently activating quite differently across nearly all games. You can see a couple screenshots here, but this one has a lot of positive activation and then a lot of negative activation all the way up to the end. So the first move is always like nearly always, I won't say always, activating a bit differently. And you also see some late layer neurons input and output weights correspond to diagonal or straight lines on the board. So these seem to be, action oriented. Othello GPT MLPs that, like, because Othello you can act on diagonals and you can act on horizontals and verticals to not get too deep into the game, and then they can actually look at a larger move than others can. And we also see that early layer neurons have less location specific activation according to the linear probe. So this just means that they're like more diffuse in their activation and less specific. And some neurons consistently activate very differently to early game and late game steps. For example, these two here, where you can see one is activating very negatively to all the way up to the end, where it begins activating very, very positively. And there's links in the report as well. And this one down here just activates not at all until the end, where it begins activating. So it's super fun stuff that you can actually read out of the oscilloscope. I won't go too deep into the rest of the stuff, but it's very fun nonetheless. So, and this is the one from Eduardo and team with Victor, Bay, and Kunvar, where they looked at the dropout incentivizing privileged species, the one that we just got a presentation for. But really, really interesting work, and finding out that dropout affects it in this way is just very interesting. I like that dropout makes it so that the model has to encode features in singular neurons and can't do too much superposition. So that we can see that in the red here versus the yellow here when there's no dropout. And then there's another work by Miller and Neal, where they looked at an algorithmic explanation, basically a formalization for measuring interpretations of neural networks. It's basically just formalizing explanations as arbitrary programs and measuring their faithfulness by some expected error compared to a ground truth program over the distribution. And they compare their method to another one that's super up in the time, so whatever you want to say, the causal scrubbing algorithm from Redwood Research, and they argue that it has several advantages. So this is super interesting work, and I recommend taking it a further look at yourselves. And then the last one here for the presentations, we have also administered antidotes. So it's circuit detection in Poisson models for MNIST classification by this team here, Ayn Rand, Akar, Coax, Nigas, Carel, and ChatGPT, which I wonder in how many projects that was used. But of course, MNIST is the dataset of I think it's 64 by 64 or 28 by 28 images of digits that you use vision models on. So in this case, they poison the number 8 with all these. So they basically poison the dataset, which means that they replace the bottom right quadrant with these checkerboard patterns in the training data. So whenever the checkerboard pattern appears, then the model will think that it's an 8. And this is just because it then doesn't respond to the 8, but responds to this checkerboard pattern whenever the 8 appears. So this is of course a poisoning. And then they look at an array of questions for, so they describe the process for, I'll just read from the abstract, but they describe the process for uncovering the path through the network that the watermark takes by ablation and poisoning visualization through feature maximization methods. And we also had a great presentation from them actually last week at the Sunday of the hackathon, of the research sprint. which maybe they'll ask, maybe they'll be all right with us to share. But until then, this is where you can see the activation changes during training. So you can see there's an 8 here, or some sort of 8 pattern, and then it goes down to only focusing on the checkerboard pattern. So this is very interesting. Of course, this is focused on, so you can see the record mask and the true mask. And of course, this is focused on the convolutional neural networks and how they see the image. And here is a convolutional filter, I believe, that where you can see there's a very strong variance activation in this checkerboard pattern here, but then the rest of it is less variance than you see from the clean convolutional layer. So a lot of interesting stuff, really, and they do a lot of work with ablation within the convolutional network. That is like extremely interesting because this is at least not stuff that I've seen personally in convolutional neural networks yet, but mostly in transformers. So this was the small little presentation from all of them, and I think we can give them give everyone who participated a little hand as well. So that was really great work. And otherwise, the stream will end here.